Hi, I'm Matt Diefenderfer, a data scientist in research computing at UAB. Today we're going to be taking a look at Fmriprep, a pre-processing pipeline for structural and functional MRI data. This pipeline will take BIDS formatted unprocessed data and convert it to a format that is ready for data analysis. So it performs a set of pre-processing steps on your fMRI data that we're going to go over here in a little while. For questions about how this processing pipeline works that this video may not cover, you can go to fmriprep.org up here. It'll take you to fMriprep's documentation, where you can read through the various details, the outputs, usage notes, and get pretty much any answers that you need about how to enable, disable, or alter any steps of the pipeline. Also, if you go to uab-cinl.github.io, we have some condensed documentation about how to use Fmriprep on Cheaha, including some example Fmriprep scripts that we are going to go over later on in the video. Okay, so let's go over some of the steps that Fmriprep includes in its pre-processing pipeline for structural and functional data. So to begin with, it will start with your structural data. For structural pre-processing, you are only required to have a single T1 image. However, you can have multiple T1 images if you've acquired multiple during a scan session, and it can also incorporate T2 weighted images as well. So it'll begin by taking your T1 weighted image. It'll perform intensity normalization on the T1. It will then, if you have multiple T1 images, it will average all of them together to create a single reference image. It will then skull strip the image, and then it will take it through the basic FreeSurfer pipeline. The FreeSurfer pipeline is where it will spatially normalize the data to the FS average template. It will also do brain tissue segmentation for the white matter surface and the peel surface, and then turn those into 3D models. This brain tissue segmentation step is where the T2 weighted image comes into play. FreeSurfer can use the T2 weighted image in order to better estimate the peel surface location. So if you have T2 weighted data, I would highly suggest you incorporate the T2 weighted data into this pipeline as well. You don't need to do anything special for that. As long as the T2 weighted scans are in the BIDS format and included in the subjects directory, they should be automatically included in this structural pipeline. In this same structural pipeline, as well as conforming the structural data to the FS average template, just again, the basic step in the FreeSurfer pipeline, you can also create a registration from a native structural space to any number of templates included in the template flow directory, or the template flow repository. So template flow is a large collection of normalized templates such as M&I templates, the FS average templates, FSLR from Connectome Workbench, and pretty much any other template that you can think of. All of these templates are also included at various voxel sizes, various resolutions, and then various versions of those templates. So what I would suggest is you go to the Template Flow website, look through the templates that you would want to use in your data. If you want to conform your data to the standard M&I space template, to the FSLR template, to whatever you want, look through those templates, and you can include those as options in the --output spaces option whenever you're running Fmriprep. We'll go over that later on in the video when we're talking about the example scripts that we have. So that's the basic rundown for the structural pipeline. It's really pretty much just FreeSurfer, the FreeSurfer pipeline, with an additional step for template flow if you are conforming to specific templates that are not FS average. For the functional pipeline, it does what is considered minimal pre-processing. So this is very similar to HCP pipelines. It just includes the functional pre-processing steps that are generally considered absolutely necessary to get data from a raw format to a format that is ready for analysis. After Fmriprep is done, you can perform further pre-processing steps on the outputs of Fmriprep if you want. but it's only going to do the absolutely required steps that people generally agree on. So these steps include things like motion correction, slice timing correction. It will take B0 field maps, so spin echo field maps off the Prisma scanner or various other forms of field maps, and apply susceptibility distortion correction onto the functional data. It will then convert the functional data to structural space, to native T1 space, as well as to give you functional data in any of the output spaces that you specify from template flow. So that's the basic run through for the functional pipeline. Again, it's not too many steps. It will create also a list of confounds that you can use to regress out in your further analyses. It doesn't do it automatically, but they are available for you, and we can talk about that in the output section. So overall, again, it is a minimal pre-processing pipeline, but you don't need to know how to perform each individual step. This pipeline does take multiple tools, such as ants, FreeSurfer, like I listed before, FSL, and whatever they deemed as the best tool to perform any specific step in this pipeline. They have taken all of these tools and combined them together. That's one nice thing about Fmriprep, is that as further tools are developed to improve upon these methods, new versions of Fmriprep will use those newer tools to make the pipeline as good as possible, pretty much. So before we go over how to run Fmriprep on Cheaha, I just want to go over an example dataset that we're going to be using later on in the video. So the way that I have my data structured is I have an overall dataset directory here. For example, this one's just called D01. Inside D01, we have both raw data contained inside the DICOMS folder, and then we have bids formatted data inside the Nifty folder. This was the output folder for the HeidiConv tool that I used to automatically convert the raw data to a bids format. Fmriprep is going to draw its inputs from this Nifty folder here. And then we also have a working directory for Fmriprep working files that it's going to create during processing that we'll go over here in just a little bit. Inside this bids formatted directory, if we go in here, we can see that we have two subjects, sub S01 and sub S02, as well as the output participants TSV and JSON files, and a task-related bold information in the form of a JSON file down here, as well as the dataset description file that is common to all bids outputs. That I showed you previously, we do have a section on Fmriprep here. So using Fmriprep on Cheaha has a lot of information, a lot of what I deemed important information for actually running Fmriprep here. You can read through that. We do have Fmriprep installed as a module already, so you don't need to download it. All you need to do in order to have access to it is run this module load command here. But if you want to read through this page, it'll give you a lot of information about how to run Fmriprep, what each of the options are for, everything like that. One of the other resources that we have here are example Fmriprep scripts. And I kind of just want to go through the scripts themselves to give you a general idea of what each of these are doing. Now, you could, if you wanted to, just copy paste this script into Cheaha, run it directly from that. You would really just need to change a couple of things, such as the dataset directory here and the participant name. But if your data's bids formatted, you could just change these two things and run this script as is, and it will run completely fine with the options that I've set in here already. But let's just go through what some of these options are. So first off, let's talk about the actual job parameters that you're requesting. So what I have here, I've requested a single task. I've requested 4 CPUs for the job. So Fmriprep can take advantage of multiple CPUs up to a certain point. In my experience, requesting 4 CPUs and then 5 gigs of RAM per CPU, so for a total of 20 gigs of RAM, is generally good enough to run through a number of pre-processing steps for, say, 4 or 5 functional scans in about 2 hours. That's not including time to perform FreeSurfer. FreeSurfer takes a number of hours longer. In my experience, 7 to 8 hours would be a good number to allocate, but can take up to 24 hours or even more. So in my case, I requested 50 hours of time just because I didn't know exactly how long the reconstruction FreeSurfer was going to take. But 4 CPUs and 5 gigs per CPU is typically good enough for an Fmriprep job, and it will schedule pretty quickly. In here, I've also set the dataset directory, so that's going to be the overall dataset directory. So in our example, that was the directory above the bids formatted directory. I've also set the name of the participant here, so in our case, P01 for the example here. It then loads the module and then runs the Fmriprep command. So it uses a couple of options in here, and we'll walk through each one step by step. So first, it sets the working directory. The working directory is essentially just a place for temporary files that Fmriprep creates during all of the steps. It should delete these files as they are when they're not being used anymore, but it's good practice to go in there and check and make sure. But everything in the working directory after the jobs are completed are not necessary, and you can remove them. But it just provides the pipeline a place to actually put these temporary files. The next one is the participant label. So by default, if you don't set a participant label, Fmriprep is going to try and run processing on every single subject inside that bids formatted directory. And that's just not going to be time efficient. If you have more than one subject that you're wanting to run through Fmriprep, we have a solution for that we'll go over here in just a minute. But we're pretty much always going to be using this participant label here, this participant label option, to just set it to do a single participant. And in this case, P01, like I said previously. The next option that I've set here is the output spaces option. So what space do you want your bold data in? In my case, I set it to be T1W, so this is just telling it to put all of my bold data into native T1 space. But if you wanted to put your data into a standardized space, such as M&I space, this would be the option. You would put the template that you wanted your data converted to in this output spaces option here. And you can list multiple. You can list T1W and any other template that you wanted in a comma separated list here. It doesn't have to be just a single output space. The FS license file option here refers to the FreeSurfer license file. If you are performing Recon All to do surface reconstruction on your structural data, you are going to need access to the FreeSurfer license file. There are instructions in this using Fmriprep on Cheaha page here. For if you click on FreeSurfer license file, it'll take you to a small section where it'll give you instructions on how to copy the license file from the module to a location that you're going to have permanent access to. And then in the script, you will just list the path to the license file that you copied. In my case, I copied it to my home directory, so I'm always going to have access to it there. And just so you know, the license file, it doesn't have to be, or is not FreeSurfer version specific. You can use any FreeSurfer license file for any version of FreeSurfer. The next option that I've set here is the number of CPUs. It's just going to match the number of CPUs that I requested up here, and it's just letting Fmriprep know that it has access to more than one CPU to help speed up processing. The OPMN threads here just tells it how many threads that it has access to. I just set it again to 4 to match the number of CPUs. And then the last option here is the SIFTY output space option. So if you're wanting to use tools such as Connectome Workbench or the Workbench view in order to create plots or whatever you want, you're going to need to transform your data into Sifty space. In my case, I want to transform it to Sifty space, and I put 91K here. Just so you know, for Fmriprep, the 91K option corresponds to the FSLR standardized brain, the Connectome Workbench standardized template in its 32K mesh. Okay, so 32,000 vertices per hemisphere and then subcortical. It's 91K in Fmriprep. And then all of these options with the double dashes in front of them are optional. You don't have to include them, but the last three options down here are required. So the first option in here is going to be the BIDS formatted directory where Fmriprep is going to find the data to work with. So in my case, I just set it to be the dataset directory / Nifty. So Nifty was the BIDS formatted data. The next thing that it needs is a place to put the outputs. In BIDS formatting, any derived data from the BIDS formatted data should go into a derivatives folder. In my case, I put the derivatives folder into the Nifty folder, into the BIDS formatted dataset folder. And then the last option here, just leave it as participant. It's just telling Fmriprep what level to perform its analyses on, or its pre-processing steps on. The only option available right now is participant, so just leave that as participant. So that is going to be the single subject script. Like I said before, and for many people, you're probably going to want to be pre-processing more than one subject at a time. Say you've collected 10 subjects or 100 subjects or whatever, and you want to do all of it at once, but you don't want to do it sequentially because it's going to take absolutely forever. What we have down here is an example array job script. So the array job script is going to perform functionally identically to the single subject script, except instead of naming a single subject to perform the preprocessing on, it's going to instead access the participants.tsv file inside the BIDS formatted dataset. So if we take a look at it in our BIDS formatted dataset, we have the participants.tsv file here. If we take a look at what's inside it, it's going to have a list of the BIDS formatted subjects in it. Okay, it's just going to have sub S01 and sub S02 in the order that I converted them to BIDS to the BIDS format originally. But it's going to go into that participants TSV file, read all of these subject names from it, and then essentially replicate this Fmriprep script for each subject and submit all of them at once. So you're going to have each subject running in parallel on the cluster. So hopefully it won't take absolutely forever to run through an entire dataset if you're wanting to perform Fmriprep pre-processing on it. So the setup for the script, is, like I said before, is functionally identical to the single subject script. We've got 4 CPUs per task, 50 hours on the medium partition, 5 gigs per CPU. The only things that have really changed are the job name and then the output text file. So the job name is going to be Fmriprep, and then a %a that represents the array index, and we'll talk about the array index here in a second. The output job name is pretty much the same. It's going to be called Fmriprep dash, and then the main job number, and then the array job index, and then .text. And that's going to just be put in the same directory that the Fmriprep script is run from. The only things that you really need to change to run this script, similar to previously, is the dataset directory. So you just need to give it the path to the dataset directory and then the BIDS formatted Nifty directory. In my case, it's the same as before, D01, and then the Nifty directory is the BIDS formatted directory. In order to run the array job script, it's going to be a little bit different. So to run the single subject script, all you need to do is say sbatch and then the name of the script in the command line. That'll submit the job script to the cluster for scheduling and then for running. For submitting the array job script, you do need to add an extra option whenever you're submitting it. So it'll be sbatch, and then you'll give it this -- array option. Now, the -- array option is going to tell the scheduler which subjects you're going to be processing. So, and that's going to be dependent on where they are inside the participants.tsv file. So if I wanted to run just subject S01, or if I want, in this case, let's say I wanted to run subject S01 and subject S02 through Fmriprep, the command that I would run to submit that job would be sbatch and then -- array equals, and then it's going to be actually 0-1 here, because the index is zeros based. So if I wanted to run the first and second subjects inside the participants.tsv file, I would give it 0-1 here for the array. And then you would just give it the name of the job script and submit that. Okay? If you have any questions or concerns about how to run an array job, please come to Research Computing office hours on either Monday or Thursday. If you go to uabrc.github.io, this is the Research Computing documentation. It has links to the Zoom channel, to the Zoom meetings that we have on Mondays and Thursdays from 10 to 12. Just to answer any questions that you all have about running anything on Cheaha. So if you have questions about running the array job script for Fmriprep, please come to those office hours and we'll be happy to help you. All right, so we've run Fmriprep on these example subjects using the scripts that we've went over in the CINL documentation. So let's take a look at what the outputs were. And just as a reminder for our script, we only specified an output space of T1 of the native T1 space, but we also specified a SIFTY output that would be put on to essentially the FSLR 32K atlas. So we should expect outputs in both native T1 space as well as in that FSLR 32K space. So remember, in our script, we specified that our output should be put into the derivatives folder inside the bids formatted directory. So if we go into derivatives here, we can see that we have two separate output folders, one for basic FreeSurfer output and then one for the Fmriprep output. So the FreeSurfer output is just going to contain your basic FreeSurfer output as it says. So if you go in here, you can find all of the FreeSurfer surfaces, the MRI images, the volumetric images, as well as all of the standard atlases and labels that come along with FreeSurfer by default. So I'm not going to go through all of that, but I would highly suggest people go through and learn how to use FreeSurfer. It is a very useful tool for structural analysis. But if we go to our Fmriprep output, you can see that we have our one subject that we ran. We also have an HTML file for the subject that we processed. This HTML file contains a large amount of information that we can go through pretty quickly. The HTML file will just be opened up in a Mozilla Firefox window inside FreeSurfer. If you export this HTML file to your local desktop, it'll open up in whatever browser you have as your default browser. It's an HTML file, so it should open up perfectly fine no matter what. It gives you a large amount of information about what happened during the processing pipeline. So it gives you an overall summary for the subject, the number of structural scans that we had. So like we said before, we only had one T1 weighted scan. The number of functional scans, as well as the standard output spaces that are listed by default. So it, by default, creates transformations for MNI 152 space. But since we did not specify that in our output spaces, it does not convert our data to that space, which we'll see here in a second. It also lists the non-standard output spaces that we listed in our command, so native T1 space here. And then it says whether we performed FreeSurfer reconstruction, and you can see that we did run it FreeSurfer through Fmriprep. But again, there is the choice to not run FreeSurfer if you want. All right, so if we take a look at the anatomical section of this HTML file, we can see that it gives us a good overview of the surfaces as well as the brain mask that were created by FreeSurfer. So you can see the white matter surface delineated in blue here, as well as the brain mask outline delineated in red. So you can go through and see if there was any dura that was included in the brain mask or not, and how well that performed. If we scroll down, we can also see a spatial normalization of the anatomical to a M&I reference space. So if you have your mouse hovered over the image, the images will flicker back and forth between participant space as well as M&I 152 space, so that you can see how well those two, how well the native space got registered to the standard space. You can see here that the registration was performed pretty well overall. I'm pretty happy with that. If we go down, it's also doing the same thing from participant space to a different M&I space. Just both of these M&I spaces are included standard in the Fmriprep pipeline, but it just gives you a good idea of how well the registration was performed. There was also a surface reconstruction overview here, so we can see the white matter surface in blue as well as the peel surface in red, and how well FreeSurfer was able to delineate those surfaces, how well it was able to create those surfaces. We also have functional output, so this is a susceptibility distortion correction image, so it shows you before and after for the distortion correction for the functional images. You can see as it flickers back and forth that the images for before distortion correction had some squishing at the anterior portion of the brain that was then corrected and elongated after distortion correction using the spin echo field maps. Then we also have the report for how well BB register aligned the functional and anatomical MRI in native space. So again, if you hover over, it will show you the functional space overlaid on top of the anatomical surfaces that were created. If we go down, we can see on these main sagittal images that it looks like the surfaces were aligned fairly well between our structural and functional data. So by default, Fmriprep also applies CompCore to all functional data that is run through the pipeline. So it gives you this in a graphical format inside this HTML file, and then CompCore outputs are also output into a text file that is included in the outputs. The components that are determined from CompCore are not automatically removed from any data, but they are listed for you to do with as you will later on your own. So you can read through all of these outputs for the bold summary for the CompCore outputs and the correlation among the nuisance regressors to get some more information about what is happening inside each of your bold scans. And it does this again for each of the bold scans that we have acquired. It lists the susceptibility distortion correction, the alignment between functional and structural scans, as well as the CompCore ROIs. Okay, so we've gone through the HTML file, which has a lot of diagnostic information for what happened during the pipeline, and I would highly suggest you look through each of the composite HTML files for each subject, just to make sure that everything ran the way that you wanted it to. But we also have a folder that contains all of the outputs that we wanted from our pipeline in it outside of the FreeSurfer outputs that we looked at earlier. So let's take a look. So inside the subject folder, we have 4 other folders: an anatomical folder, a functional folder, and a figures folder, and then a log folder. The figures folder actually contains each piece of the overall HTML file that we just looked at. So if you wanted to send an image or a specific piece of that HTML file to somebody without actually sending the whole thing, you could just pick up, like, let's say, this single run, the registration from functional space to anatomical space. You could open up this image and send it to whoever you wanted to. So we have two other folders here that contain the data that we want to look at from the outputs of Fmriprep, the anatomical folder and the functional folder. So if we look into the anatomical folder, it has a number of volumes and surfaces in it. The ones that we're going to look at are the pre-processed T1 image, so the native T1 that has gone through the pre-processing steps that I listed earlier. It has a brain mask file, as well as the APARC and ASEG that are created from FreeSurfer in volumetric format. So if we, for instance, if we wanted to look at those, we could, in a command window, do a module load FSL 6.0.3, execute that. It's going to tell us to source a file. And we're doing this so that we can use FSL's viewer FSL eyes. So we can open that up after sourcing that, after sourcing this file listed here. We can open up the FSL eyes viewer using the FSL eyes command, and it'll take a minute to load up. So we have FSL eyes loaded up here. Now we can add from file. We can go to our nifty folder, our bids formatted folder here, into the derivatives, into Fmriprep, our subject, and then our anatomical directory. And we want to go ahead and load the pre-processed T1 image just as an overlay. And then we can look at, let's say, the ASEG here. So if we wanted to open those up in FSL, those will load up pretty quickly. We'll put the pre-processed T1 on bottom just as a bottom layer. And we can look through it. It looks like everything looks pretty good in this image. And say if we wanted to look at the segmentation here, we can go up to this drop-down menu up here with the ASEG selected and change this to a label image, because the ASEG is a set of labels. That'll change it to a lookup table with the white matter, peel surface, and then various subcortical delineated regions set up in different colors. If you want to change the lookup table, you can. I would suggest something like the random is fine, but the MGH CMA FreeSurfer is going to match what the FreeSurfer colors are going to be if you loaded this up there. And you can click through and see which voxels or which regions are assigned to which anatomical structure. So the point that we have selected here is assigned to the left thalamus proper. It also gives you a good overview of where the cortical region is. So it's left cerebral cortex or right cerebral cortex, or just white matter that is not part of a subcortical structure. And we can click the view on and off to see how well the white matter and gray matter seem to be segmented in here. Also in this folder, we have various surfaces that were created in Gifty format. So these can be used for projecting the surface-based functional files on. So we have the inflated surface, a mid-thickness surface, a peel surface, and then a smooth white matter surface for both the left hemisphere and right hemisphere. We also have CSF gray matter and white matter segmentation masks that we could look at in FSLIs as well. And then we have a list of transforms from various spaces to native space, or from native space to other spaces. So the first transform is going to be from FreeSurfer native space to actual native T1 anatomical space. We also have MNI space to native T1 anatomical space, and then another version of the MNI template from that space to native T1, and then the same transforms but in the opposite direction. So native T1 to FS native to MNI, to this MNI template, and then to this other MNI template. Those are just created automatically, so you don't need to create another transform using BB Register on your own. These are just there for you to use if you need them. So like I said previously, we also have the functional output folder. So if we look in that, we have the confounds time series. So back there when I was going over the pipeline, I said that it would output the confounds. You can find the TSV file for containing all of the confounds inside this func output folder. If we opened it up in OpenOffice here, we can see that we have columns for each of the confounds that it extracted during pre-processing. So we have global signal, we have CSF signal, white matter signal, and then all of the comp core components that were created during that part of the pre-processing pipeline. And then each of these are given as a time series. So each of the rows past the first one corresponds to the volume. So second row is the first volume, third row is the second volume, and so on and so forth. We can see that we have, if we go down to the bottom here, we have 421 rows for our 420 volumes. So 420 rows of data, not counting this first one. So you can come in and get any of the confounds that you need for your analysis, or if you want to regress them out as further pre-processing, you can come and grab them from this TSV file here. So we also have, since in our call to Fmriprep, we told it that we wanted it in a SIFT space. We also have the FSLR, so you can see the space FSLR here. We have the time series and its corresponding JSON sidecar file on the FSLR 32K mesh. So you could load up the FSLR 32K mesh and then overlay this time series on top of it to scroll through and take a look at it. You also have all of the volumes down here. So you have the pre-processed bold volume here. You have the brain mask for that, all in native T1 space. And then you have the aparc aseg file overlaid on top in the same space as the pre-processed bold. So we can see that if we loaded those up in FSLIs, we can add from file here, go to our functional folder, load up the pre-processed bold scan as well as the aparc aseg, and it'll load up those two files here. We'll move the pre-processed bold to the bottom. We will do what we did before, change this aparc aseg layer to a label image, and then change it to the free surfer color lookup table. And you can see that each of these voxels are overlaid on which area they correspond to in the bold image. So you can use this as a pretty good ready-made way to create masks, to create area masks for any area that you're interested in. So let's say that you were interested in the bold series or doing analysis in the caudal middle frontal area here. You could go into this brain mask, find the voxels that have code 1003, and create a mask from those. And then that'll find the voxels in the preprocessed bold time series in that area. You can do whatever analysis you want to do with those voxels. So those are the outputs for the single scan for the first resting state scan that we've performed. We also have the exact same outputs for the second resting state scan. You can tell from the name, it has the same BIDS formatted names that we were used to previously. So that is really the run through. You can customize the Fmriprep command in any number of ways, adding or removing steps, and customizing the output in whatever space you wanted. So if you wanted it in an MNI space, it would create pretty much the same set of files, except instead of having a space-T1W here, it would be a space-MNI. Again, like I said previously, you can combine spaces to where it outputs both native T1 space, an FSLR space, an MNI space, and whatever else you list in the command. If you, like I said before, if you have any other questions about it, please go to fmriprep.org, read through the documentation that they have ready for you here. If you have other questions about running Fmriprep on Cheaha, and our guide at uab-cinl.github.io does not answer those questions, please drop by to Research Computing office hours. So if you go to uabrc.github.io, on the front page here, we have links to Research Computing's Mondays and Thursdays office hours from 10 to 12. Drop in. I should be there. Let me know, and we can work through any problems that you're encountering using Fmriprep. I hope this video has been helpful for you, and I hope that you all have a great day.